Okay, no problem. Yes. So welcome to the Big Data Health Science Center, the seminar sequence. And today, so this seminar is organized by Electronic Health Record Call. And today's speaker is Dr. Yufeng Liu from North Carolina Chapel Hill. And he lists several departments on his web page. So he served as faculty member for the Department of Statistics and Operation Research, and Department of Genetics and Biostatistics, and also work on the Center for the Genomic Science and the Cancer Center. So lots of the services are the affiliation for him. And Dr. Liu's research focuses on the statistical machine learning and data science, high-dimensional data analysis, and the personalized medicine, and neuroimaging data analysis, bioinformatics. He served actually as editor and associate editor for the STAT and Annals of Applied Statistics, Canada's Journal of Statistics, Journal of Multivariate Analysis, and the Royal Statistical Society Series B. So it is actually very exciting to have him to share his research with us in data science. He will talk about the learning individualized treatment rules with many treatments. So before we start, I just want to remind you that we will save all the questions at the end of the presentation. If you have any question for Dr. Liu, you can send it anytime by putting the Q&A button and also enter your question. If at the end, you can also raise your hand and be invited to unmute and ask a question at the end of the talk. So thank you, and let us start.
Thank you so much, Jia, for the kind invitation and the introduction. And thanks, Miranda, for arranging everything to make it smoothly. So it's a pleasure for me to share some recent research. Let me do the full screen mode. All right. So this is some very recent work joined with PhD student Haixu Ma and my colleague Donglin Zeng at the UNC Chapel Hill. This work just recently accepted by the NEURPS, happened a couple of weeks ago in New Orleans. Yeah. Okay. So today I will talk about individual treatment rule problem, but the setting with possibly many treatments. Okay. So just a quick introduction. The example setting we are consider is personalized medicine. We know traditional medicine, or often the time, is one size fits all. I guess this picture is not exactly accurate. The current medicine, we have some precision medicine as well, but the one size fits all is that no matter who comes in, for example, colon cancer, they all get the same treatment. And unfortunately, because of heterogeneity in human population, some may be effective. It may be effective for some people, may be no effect, or maybe some adverse effect for some other people. Then the idealized medicine, which we also call it precision medicine, is to utilize the individual information, for example, the blood, DNA, and so on, so that we can get the best personalized treatment tailored for subgroup of people to get the best effect. So it's transit from the one size fits all to individualized medicine. Okay, so I will use this medicine application as an example. However, the method I will talk about it can be used for generalized decision making. So it could be some other setting, like in financial application and so on. So it does not have to be only for personalized medicine application, although this is a natural place to apply. Okay, so individual decision making in general is we try to make personalized decisions based on individual information. For example, we can try to do personalized advertisements, especially for e-commerce application, or we can do personalized studying or education based on the background information and so on. But in general, the goal is to find the best decision, which in the sense the best is you have certain criteria we are trying to optimize. So we want to be the best decision with respect to certain criteria. So in the precision medicine application, as I was talking about earlier, we could consider, say, in the individualized cancer treatment, we want to tailor therapy based on the genomic information of the individual patient to optimize the future health of the patient. And in fact, there's already a case study for different cancer treatment. For example, certain subtype of breast cancer, the chemotherapy may not be effective, but in that case, if we have that information, we can have better treatment for the patient. All right, so in the literature for individualized treatment rule, there are many methods available. There are perhaps two major group of methods. One we call the indirect learning. In the sense, there are two steps involved. The first step is we can try to estimate the treatment effect related to using certain outcome in model. So you can consider I'm trying to estimate the effect for each treatment. And then the second step is to decide which one gave the best rule. So that's the two-step procedure for indirect learning. There are various methods involved in this category. For example, the well-known regression-based methods such as Q-learning, A-learning, and so on belong to this category. So in the sense, you model the outcome first, and then you can see which one gave you the best rule. Then, in contrast, there are also methods known as the indirect method, direct method. That's the case that you don't have to estimate the effect first in order to decide the rule. Instead, you can directly get the best rule. For example, there's method along this category by recasting the problem as some sort of weighted classification problem, and then you directly estimate the rule without estimating the individual effect size. So the motivation for what we are doing today is in some applications, you could have many treatments available. However, the observations you have may be limited. So then there's some difficulty because there are so many treatments. For example, I'm going to use this PDX study, which have more than 20 treatments. There are also issues that if often the time you possibly have the data to be quite unbalanced. For example, you may have certain treatments, the number of patients relatively small compared to other treatments. This especially can happen if you have many treatments, and that can create a difficulty. So in that case, the natural question is, how can we effectively estimate the optimal ITR in this case? Another motivation is that often the time when you have lots of treatments, it is possible that certain treatment may have similar effect. And then people may consider to cluster these treatments so that for the treatment with similar effect, you want to cluster together. But then for treatment different, you want to put it in different clusters. So our motivation, consider these two issues. You have many treatments, and then possibly maybe we can cluster the similar one together. So that's what we are trying to address. However, the existing methods, if you trying to use the existing either direct or indirect approach, you have to model all these treatments together because there are so many of them that can create a large variability and instability. And if you want to cluster them, there's really not, as far as we know, not many methods available to dealing with this method, especially the case when you have many treatments. So we try to address this problem in a different way. So what we try to do as a main contribution is we propose something called the supervised clustering to handle the many treatments. So by its name, I'm sure many of you are familiar with the machine learning terminology. Clustering is a typical unsupervised learning problem, which you do not have the response. And the supervised learning is you do have response. So here we started doing something in between, we call it supervised clustering, essentially combining both together. The supervised part is referring to I'm estimating the ITR, so that's a supervised learning problem. And the unsupervised part is referring to the clustering treatments, because I have many treatments. We want to do this together in one objective function. So then the goal is to cluster the relationship rather than the standard clustering. You just cluster them according to how similar they are. Here we are trying to cluster according to the relationship. That is the response versus the covariance and the treatment interaction. So really what it means is that I want to cluster those treatments have similar relationship with the covariant treatment interaction, so we can group them together. So essentially, we end up being able to formulate the problem as a convex minimization problem involving certain laws to quantify the goodness fit, and then a fusing penalty try to encourage fuse of similar treatment together as a cluster. And the one nice feature of what we are our method is that because we have a convex minimization problem, we eventually can get entire solution paths with respect to the tuning parameter, which end up being able to give us a clustering process as almost like a dendrogram you typically see in clustering analysis. So we can use the bottom-up approach so that rather than seeing observations clustered together in the traditional clustering, here we will see treatments are being clustered together as a group of treatments. Okay. So now I will tell you how exactly we can achieve this. Okay, so that before we move on, let me give you some notations to talk about the setup of the problem. So we consider the data as triplets, Z, A, and Y. Z is the features, which is a p-dimensional feature. You can consider the features including, say, genomic information, clinical information, and so on of the patient. And then A is the assigned treatment. For example, I can consider M different treatments. So here M could be fairly large, all right? In the traditional setting, you may consider, say, 2 treatments, 3 treatments, so on. Here, my M can be much larger than that. And then Y is the response, using the reinforcement learning literature terminology, we can also call it the reward, then the larger the better. Because the treatments, an individual may only get one treatment, then if we want to look at all possible treatments, so there's a potential outcome YA, meaning what if you give label A to that patient, then the outcome going to be that's the potential outcome. So it may not occur in practice, in reality, but that's what would happen. That's the potential outcome. And then the probability of treatment A given Z is a propensity score. And our goal is to learn this individualized treatment rule, capital D, which is a mapping from the covariance space for the Z to the treatment space A. Now, in the literature, Chen and Murphy in 2011 considered the value function as the expected outcome given the rule D. So the goal is to make this the larger the better because the reward is the larger the better. So we want to find a rule D star, which is the optimal rule D, to maximize the value. So I want to find a D to make the value largest. That's the D star. And my goal is to learn the optimal ITR. Okay. And there's a typical causal assumptions involved, which I won't get into detail, but this causal assumption ensures we have identifiable value function. And then the optimal ITR D star is really to get the best value that which is equivalent to say I want to find the best expected Y given Z and A. So this is essentially because I'm considering the different Z, which is the covariant information or contextual information. Therefore, I can model the heterogeneous treatment effect. So once we say given a patient, I know how these different expected outcome given different A, then of course we're gonna know which A is the best for that individual patient. Okay, so this is relatively intuitive. So now the setup for us is consider the regression model. The Y is the outcome, and the covariance is the Z, and then we also have the treatment A. So we're gonna have a term without the treatment, so that's the main effect term, or known as the treatment-free effect term, as well as the treatment and the Z interaction part. This is called the interaction effect. So you can see I have the covariance Z and the treatment A. So that's the interaction effect, subject to some constraints. So for the identifiability, we want the interaction to sum to 0. And then we want the error to be mean-centered, to have mean 0, and then the variance to be bounded. So the zeta parameter zeta A characterizes the interaction effect of each treatment A, because it's characterized how does it related to the covariance. And then we have the sum to 0 constraint to ensure the identifiability. And we want to, again, get the best rule given our data, which is the D hat. Okay, so argmax the T, because remember, we want the outcome to be largest with respect to your treatment A. However, the main effect have nothing to do with A. Therefore, what you really end up need to be focusing on is this T, the interaction effect. Okay, so now with the setup, let's consider our method. Our method, the idea is if we have similar treatment effects, we will likely to have similar parameter, the interaction effect parameter zeta A. And then if you have similar parameter, you can try to cluster those treatments by fusing them together. So in other words, if I have two treatments, the interaction effect parameter are the same, then I can put the treatment together as one cluster because they have the same effect. But in general, if they are not the same, if they are similar, you can put together. That can happen by doing so-called fusing later I will talk about. And we will focus on the residual by removing the main effect, since the main effect is not related to your rule. And here, for illustration, I'm just consider linear model. However, the idea can be generalized to a more complex model as well. And then I can consider concatenate the parameter zeta, which really put all the M of them together. Remember, M is the number of treatments. So each zeta represents a parameter for each treatment. I have M of them. So there's M subvector here for the whole zeta parameter. And now the objective we are considering here is the first one is just the typical loss function. You can consider, for example, least square loss and so on to characterize the model fitting. The second term is I'm trying to do pairwise fusing of different groups, different treatments. So for example, treatment L, treatment T, I want to fuse their difference. Then if their difference end up to be 0, they will be in the same group. Okay, so just to relate to these notations, so the L here is the loss, and then I have L1 norm here, and the P is some sort of penalty function to encourage grouping of my parameter, and lambda is a tuning parameter, and En is the empirical mean. So the interpretation here is kind of similar to standard regularization framework, although we have a little bit twist for treatment here, is we want to maximize goodness fit, but at the same time, we want to minimize heterogeneity among treatments. Okay, so when I say heterogeneity is when the treatments have different effects, I want to group things together. Okay, so a little bit more notation, because remember the Z is our covariance, and we could have certain elements of Z contribute to the interaction term, but some may not contribute. So here I'm dividing into X and the V. So X will be the covariates specifically contribute to the interaction term, but V are the term covariates do not affect the interaction, meaning they only show up in the main effect. I will talk about later how do I divide them, but assuming I know this now, so then the Z can be written into two parts. So for simplicity, I can use the first D of them to represent to be X, and then the remaining P minus D of them to be the V. And then the parameter I can group into two parts. The first part is the beta parameter related to the heterogeneous one, which is related to the interaction term. And the gamma is a common across, okay? So then my zeta have two parts, beta and the gamma. And then beta and the gamma corresponding to X and the V. And I'm considering residual by subtracting the main effect term out. Therefore, the interaction, the main effect term, the true regression coefficient should be 0, because if it's not 0, it's going to be removed from the main effect term. So therefore, right now, the true parameter for gamma should be 0 after I center the outcome by removing the main effect. So therefore, what I really need to just focus on are the betas, because the gammas are really can be subtracted out. So next, I will need to consider we need to classify Z to be X and V, and then we can use group lasso-based algorithm to do that. Okay, so I can rewrite my model into the following. So the main effect term is still there. The interaction term, I have X, which is the term of interest. Remember, X is related to the interaction term. And then the V here are the variables do not relate to the interaction term. So the gamma A's are all 0. Then I can simplify this to be two parts, the main effect term, both in X and V here. And then the interaction term only have X here. And that we still have all those constraints. So after distinguishing X from V, I can rewrite the objective function, again, the loss term. But then the penalty, I only need to focus on the beta. Remember, the gamma are not affecting the interaction. Therefore, I only have beta here. And then I want to minimize this. So the solution beta hat will be the my solution for the parameter in relating to the interaction term. So the gamma are out because gamma, the true one, are 0. Okay. So how do we implement this? Well, obviously, it's important to be able to group them. So recall the zeta are the original parameter concatenate together on all the M treatments. And then for each treatment label A, these are the p-dimensional parameter. And so zeta AK will be the regression coefficient for ZK, and the ZK, I have K from 1 to P, and then treatment A of 1 to M. So I have little a and little k here. I can rearranging zeta by sorting my covariate vector order. Remember, we have the parameters. I can rearranging them by sorting for each group associated with a covariate. Originally, I sorted according to treatment. I have M of them. Each zeta are p-dimensional. Now I can rewrite it as C1 to CP. Each C is M-dimensional. So in other words, C1 corresponding to covariate 1, but it's the length of M because there's the M treatment. Okay. So then, by the definition of V, all the zeta AK 0 equal to 0 for the common one. So therefore, the true coefficient C0, I can rewrite as follows. So for the first D groups, remember, I'm dividing the covariates into the treatment interaction related term, there are D of them. And then treatment-free effect, that's P minus D of them. So the first D, that's the C1 to CD. The remaining one are the gammas, those are 0. Again, each C are M dimensional related to M treatments. So I have D different groups. By doing this, I'm writing D different groups. So by writing the parameter this way, this really motivates us to implement a group lasso penalty to shrink the whole group vector CK to 0. That will achieve group sparsity. So if CK is 0, that means it's essentially corresponding to the Z. Remember that I divided Z into X and V. So if the C equal to 0, then the Z should belong to V. Otherwise, it should belong to X. So the main idea is I could use group lasso step so that I can identify whether each Z belong to X or belong to V. So that's the first step we can do, is to do a group lasso step by grouping each the parameters associated with each covariate. And then for those non-zero groups, that's essentially the one I need to be interested in. Okay. So by doing this group lasso step, I will be able to identify those interaction related terms, and then I can apply fusing penalty to those interaction related ones, and those are the beta using our previous notation. So this will make things much more effective. There's nothing wrong to apply this directly to the fusing. However, that's too many of them if you don't divide into X and V. So it will be more effective doing this group lasso step, and then you can work on the lower dimensional beta. So therefore, then fusing will become more effective for the clustering treatments. Okay, so that's the idea about the group lasso. And then in terms of after we have that, we can starting to do the fusing part, which is the beta fusing. So again, if I have my X known which covariate belong to the X, I could just do the fusing directly. So again, you could start with this directly. Then the drawback is that if your X dimension is high, then there are too many parameters to work with. The computation can be a challenge. But in general, it's okay to apply this directly. But the group lasso step is really helping to bring down the dimension for beta. Okay. So here, the fusing, you can use various different penalty. We are consider the adaptive pairwise fusing penalty by doing some weighting as well. All right, so then our problems really becoming minimizing sum of two convex functions, the loss term and the penalty term. So the loss, we just using square loss here, although it can be applicable to general loss. And then the penalty here, I'm just using pairwise L1 fusing with weighted version. And the step is that I can initialize them by using the solution with group lasso algorithm. And then I can use the initial solution by setting some weights so that I'm encouraging things are similar to have bigger weight. So I can have higher chance to force them to be 0. Otherwise, I have smaller weight. And then I can estimate given this penalty and the weights, I can then implement this. And it's a L1, it's a convex minimization problem. So we can use many existing algorithms to do this. And we use the accelerated proximal gradient algorithm to implement this. And right, so again, the weighting idea is essentially to assign treatments within the same group, and then otherwise we want a large weight for those, otherwise we want smaller weight. As I mentioned earlier, that information can be obtained by the initial solution. If they are similar, you end up as a larger weight, so they have higher chance to be the same group. Otherwise, you have smaller weight. Okay, so that's the idea of the method. And again, just to recap, the method is we are trying to do the group lasso idea to first divide the Z into X and V. X is the term or the covariates related to the treatment interaction effect, and the V are the term are treatment-free covariates. Once you divide that, then we are using fusing on the treatment interaction effect related covariates. Once you fuse them, then for the one fused in same group, it ends up to be the cluster of treatments. So that's the main idea. The advantage of doing this is, remember the challenges I talk about. Because you have so many treatments, you may end up having only a few observations for each treatment if we do the standard learning of all treatment together. But now we can sort of borrow information across similar treatments because they are becoming a cluster. Okay, so for theoretical analysis, so what's the goal here? The theoretical analysis is that we want to see whether we are doing the grouping makes sense or not, and then how about the parameter estimation? Because we have M treatment, we want to partition into K disjoint treatment groups, and in theory, we want the effect treatment within the same group identical. Although in reality, of course, you're gonna group things that have similar treatment effects rather than identical. And then beta 0 are the true regression coefficients. So we have beta 1, 0 all the way to beta M 0. Again, these are the parameters associated with the coefficient for those for X. X are the covariates related to treatment interaction effect. And then beta A0 related to the treatment A, we are assuming they are from the same treatment group, they are having the same parameter as well for theoretical analysis, meaning when they are grouped together in the theoretical analysis will assume they are identical in terms of the regression coefficient beta. So our goal here is to help develop consistency of recovering the true group structure in the sense that the beta hat converts to the true beta 0. To study that, we have it in two steps. The first step is we consider the so-called oracle estimator. That is, if I tell you the treatment group structure, what's the estimator you can obtain? That beta hat OR, meaning that's the oracle estimator. And the oracle estimator we can show, we want to first show the oracle estimator converts to the true parameter. And then the second step is to show our practical estimator beta hat equal to the oracle estimator with probability converts to 1, meaning we can identify the group correctly with probability going to 1. Okay, so this is the, I mentioned the roadmap. Now this is the two steps. The first step is we want to get the oracle estimator. So then in this case, I want to consider under the true group structure. So that I have the alpha 0 to be distinct values of beta 0. Remember the beta 0, we want corresponding to M different treatments. But if I group them into K groups, I only have K different parameters in the end because everything grouped into same group end up having the same parameter. So alpha denotes the unique ones, meaning the K different parameters for K different groups. And now I can define the oracle estimator that is given the group structure. I can get the alpha estimator. H here is the design matrix related to the true group structure. So that alpha OR hat is the oracle estimator for the unique parameter alpha. And then you can rewrite it back to the beta, which is beta hat OR, the oracle estimator for beta. So we first want to establish this oracle estimator converts to the true parameter. So that's the consistency of the oracle estimator. Okay, so we actually show that oracle estimator converts to the true parameter using under the infinity norm. Okay. So and then further we consider in terms of fusing, we consider the penalty property for the fusing, and we have the debias penalty, in the sense to remove the bias for the non-zero ones, as well as the signal need to be reasonably large, because if you this is intuitive why we need that, because if you have two groups and their parameters are very similar, that it's hard for the method to identify them as two groups. So the signal, sufficient signal, really referring to say, suppose I have 5 different groups, then you have 5 different alphas. These different alphas should be reasonably different as well. Okay, and under those assumptions, we can prove that we have a local minimizer beta hat, which is consistent in the sense conversion to the true parameter, because we first can show A equal to the oracle estimator with probability equals to 1. And together, these two steps implies that our estimator converts to the true parameter in terms of consistency. Okay. So in other words, we will be able to effectively, using our fusing penalty, identify the parameter correctly, and therefore we can identify the group as well as the parameter consistently. So that's the quick version about the theoretical study. So next me show some numerical study to illustrate the results. So remember, Z is our original features. So here I'm considering 10-dimensional features. And then for treatment, we can consider unbalanced design. That means the PA given Z is not necessarily evenly distributed. And my reward Y is a regression model. So in this case, you can see I have treatment-free effect as well as the treatment covariate interaction term. And then we consider several different scenarios. There are 10, 15, 20 treatments with 2, 3, and 4 groups. And these are let's first look at the scenario 1. We have 10 treatments, we have 2 groups, and then the 10 treatments are grouped into 2 groups, as first 5 is one group, the next 5 is another group. And then my X related to the first 2 covariates Z1 and Z2. Remember, X have are the treatment covariate related covariates, and then V are the ones treatment-free covariates. So in this case, the related to the treatments are only Z1 and Z2. So that's the interaction design we are having here. Okay. And then because we have 2 groups, the underlying truth is that if we satisfy 0.2 minus Z1 minus Z2 less than 0, we recommend group 1, otherwise it's group 2. Again, treatment within the same group, they are identical. So we consider several methods because the literature, the methods are studying all these treatments directly. So we're gonna compare with those. In other words, they are not doing grouping. So we're gonna compare with random forest. We also gonna compare penalized least square using L1 penalty. This is proposed in Chen and Murphy. And then we also use the some method by my previous students using some regression-based direct learning approach. And the lambda tuning parameter selection, we essentially using cross-validation, using the data matching with your recommended treatment, so we can estimate the value based on that. Essentially, we want to see the A match with your treatment D hat. For those, what's the value? So we use those to select lambda. The criterion we're going to compare, one is the empirical mean of the conditional treatment effect. In this case, the larger the better. We also going to compare misclassification rate. This is the smaller the better in the sense of grouping. So you want the grouping to do accurately. The other ones, we want essentially value to be large. So this picture shows the different scenario we have on the performance. So let's look at scenario 1 for now. So the first box is the random forest, and then the second one is the direct learning AD method, and then the third one is partial least square. The last one is our method by doing this supervised clustering. So in terms of the value, the larger the better. You can see, interestingly, depending on the scenario, but essentially our method can work much better because the grouping, although there are few outliers, that's the scenario, the grouping wasn't done very well. And in this particular setting, random forest doesn't work as well. And then the other two methods work similarly for the first setting. For the second setting, the partial least square, not penalized least square works pretty well. And then the other two methods doesn't work as well. And then the last case, the direct learning, the AD learning works better than the penalized regression method. And our method again works pretty well. So in general, the lesson is that our proposed method have higher value and a smaller misclassification rate. So in general, it has pretty good performance, which is not that surprising because the setting is that the treatment having groups and the other method not utilizing such group information. We take advantage of this potential group structure by grouping them together, and as a result, we can have more stable result and a better value and as well compared to the other method. Okay. So in terms of recovering the true group structure, overall we can do it pretty well in terms of identifying the groups. Okay. So you can see in scenario 1, it's the best scenario. We can have about 95% time they are identified correctly. Scenario 2 is a little bit more challenging. The worst case is a little bit over 70%. Scenario 3 is the most difficult one. The worst case is a little bit higher than 50%. But nevertheless, by utilizing this group structure, it is helping we get better results. Okay. So this is an interesting slide to explain. So let me explain this a little bit more. So remember, we have penalized approach. So we have a tuning parameter lambda, and the lambda indicating how much emphasis you put on the fusing penalty. So if lambda equals 0, that means you don't fuse them. So then every individual treatment still just be on their own. So they are not being fused. And then as I increase lambda, then things start to merge. Then we know that as my lambda big enough, what's going to happen is that everything to be fused together. So then all treatment to be one cluster. Then this gave a very interesting spectrum. So this gave us something like dendrogram looking, although it's different from the standard clustering. We can actually plot something like the clustering dendrogram to show how fusing occurs. So for example, the first case, we have 1 to 5 as one cluster, 6 to 10 as a cluster. Then in reality, what happens, it seems like I have 6, 7, 8, 10 fused together, 1, 2 fuse together, 3, 5 fuse together. And then as I increasing my lambda, they start to merge together like this. So therefore, if I choose the log lambda around here, I identify the exact grouping correctly. So that's the first scenario. And then the second scenario, I have 3 groups, and I have a case of lambda can do it perfectly well. And the third case, I have 5 different groups. Again, I can have lambda, a range of lambda to do it pretty well. So one nice thing is that the use of lambda is not like really small range of lambda can do this. You can see there's a relative large range of lambda can do reasonably good job of fusing these groups. Okay. So just as I said, when lambda increases, we can visualize the solution path. So lambda equals 0 in corresponding scenario, there's no penalty, therefore there's no clustering pattern going on. And then as I increase lambda, fusing starting to occur, therefore I can encourage similar treatment to merge together. And as I increase lambda large enough, they're gonna all fuse together. So what we're gonna do is we want to select the best lambda. And since I don't really know what the truth should be, we can use cross-validation to select lambda, which can try to hopefully recover the underlying true group structure. Okay, so this is the 3 simulation setting, which the method seems quite effective identifying the group structure. Okay, so finally, let me discuss a bit of this interesting PDX study. If you're familiar with some cancer study, this PDX data is quite interesting. So what the PDX study is about is that, you know, we all want to study cancer, but the cancer can be very heterogeneous. And we cannot really let humans say you grow tumor A, you grow tumor B, and so on for us to study. But we cannot do that. However, we can use lab animal to do, like we can use mice. So what the PDS study really doing is that we transfer the tumor pieces from human cancer to mice. And then, you know, because we can have a lot of mice to do the study, then we can really get all sorts of scenario and study all sorts of drugs. So the goal is really personalized optimal cancer treatment for different cancer among a large number of FDA-approved cancer therapies. Okay, so here, I think for PDX study, there are 5 types of cancer involved. In our case, we only focus on the colorectal cancer, the colon cancer, CRC, and we have around 850 mice from different PDX line treated with 20 different treatments. So this 20 treatments could be either single treatment, that means you only have like 1 drug and so on, or combination treatment, so you can have multiple of them putting in together. And the Y here, the outcome, is related to tumor shrinkage. So we shrink the tumor using treatment. So we you scale the maximum observed tumor shrinkage from the baseline. Of course, the larger the better, because if the tumor shrink a lot, that's indicating the treatment is effective. And the feature Z, we use 93 significant genomic biomarkers of patients for the Z. Okay, so that's the data. And this is the result using our method. The left plot showing the single treatments, and the right part showing the combination treatment. So you can see that it's interesting, the combination treatment, some of them can be better than other treatment, especially the last one. So here, before I'm showing the result, this is just showing individual treatment or combination treatment alone, how well they works. if we model with the outcome. So it shows this BYL and the BIN as a combination works the best. And then in terms of single treatment, these other treatments working pretty well. So for applying our method, we randomly split the data into, we can use 6 folds and then 5-fold to train the remaining to evaluate. And then we tune the model, tune the parameter using cross-validation. We repeat this multiple times. In this case, we repeat 200 times. So this is an interesting plot to show. This is an interesting plot to show. We have 20 treatments, and interestingly, it's classed into 3 groups with our best selected lambda. And then most combination treatments that include the BYL as a common component belong to the same group. This is essentially the green ones. You can see the BYL, BYL, BYL here. They all seem to be here. And then the BYL plus BIN, it seems to form is the treatment group itself. And then we also have another cluster over here. So our method end up recommending this single combination treatment to 92% of patients. So this is actually somewhat consistent with the previous information. We study each treatment on its own, or combination treatment on its own, with a response indicating this one to be the best one. And our grouping showing the last one, or the BYL plus BIN, itself appears to be the best treatment. And then the other one are grouped this way. Okay, so that's sort of the recommendation we can have using the method that is the BYL plus BIN. Now, what if we get rid of combination treatment? So we exclude our combination, focus on 13 single treatments, and then we can tune it among the 13. It's end up to recommend the second group around 94% of the patients. So this group. And in this group, you can see the BYL is here, and the BIN is also here. And then the first group, the HDM, LKA, I'm not that familiar with these treatments, the underlying biology, but this first one, the last one, they have fewer people being assigned there. They have smallest mean but highest variance. So the middle one appears to be better outcome, as well as variability is smaller. Okay, so for comparison, we can compare with other methods. If we use all treatments, and you can see our method can do better than the other existing methods in terms of the outcome. As well, in the case without combination treatment, we can still do a little bit better than the other method. And the random forest appears to be quite competitive in this case, but our method can do a little bit better. All right, so let me summarize what I talked about today. So today I discussed a scenario for individual treatment route selection, the setting with many treatments available. We have many treatments, and however, the treatments may have homogeneous group structure. And then if that's the setting, we can consider to group treatments, because if you directly model these treatments, then your data may not be enough for individual treatment, and then the method can lead to suboptimal performance. However, if we group as well as estimating, we can do better. So we propose this method to identify the structure by clustering the treatment together, and then learn the optimal ITR at the same time. So we adapt the idea of supervised clustering by doing convex optimization in the sense here, we are trying to cluster the treatment together. And the one nice thing about this method is that we can visualize the treatment clustering steps as a nice dendrogram. So this can show us how the treatments are grouped together. So as some extensions, right now we only consider the continuous outcome, but in many practical problems, you may have other type of outcomes such as discrete data or survival outcome. And also right now I'm only consider single stage problem. In reality, there could be multi-stage dynamic treatment problem. If you have many treatments, it'll be interesting to group them as well, and as well as learning the rule dynamically. Okay, so that summarizes what I will talk about today. I will stop here and take any questions you may have. Thank you very much.
So thank you for the nice talk, Yufeng. And so I think we're running out of the time today. And so Miranda, we have to end the session, or we can have one question?
Oh, we can have a few questions. Yeah.
Okay. Okay. So let us see whether we have any question from audience.
It will be faster if you hit the raise hand feature, and then you can actually share your question yourself instead of having to type it in the chat box.
So I do have a question for your restriction condition, Yufeng. So you have restriction condition that is summation equal to 0. How will we interpret that in practice for that restriction condition?
Say that again. I didn't.
So the restriction condition you have is summation C, I think, times Z equal to 0. What will be?
Oh.
How can we interpret that in practice for that?
So
condition?
You are talking about the model originally.
Correct.
Yeah, that's just the identifiability issue. Let me go to that slides. So you are talking, I believe.
Yeah, this is
here. Right. This is really just we are assuming the treatments because the treatments interaction effect is really like a contrast. So all we are assuming there's some, if it's not 0, you should move it to the mean effect term, because we really just need to consider the interaction as contrast. So here is really, I think it just parameter modeling. It doesn't really have a, I should say it doesn't really lose generalizability for the general modeling.
Sure, thank you.
I think there's some hands raised.
Yes, we have Alexander McLean. So I'm gonna let him speak now. So Alex, you can talk now.
Thanks, Yufeng. Really nice talk. Thank you for giving that. I had a question. This is, I think, more of a general question with IRTs than specific to your talk here, but we have a lot of outcomes in public health where we don't want them to be too high and we don't want them to be too low. You know, blood sugar, things like that. And whenever I've read some of the IRT stuff, it's never clear to me how to incorporate those kind of outcomes. Now we could just square them, but then you kind of mess up how covariates impact the outcome. It may be very clear covariate, you know, always has a positive impact on the outcome, but then when we square it, it's going to be positive or negative depending on where the outcome is. And I was just curious, is there some easy transition, you know, some easy thing you can do, or does it kind of mess a lot of the machinery here up when your outcome is not strictly one-sided, when it is two-sided, that you don't want high or low, and your optimal space is somewhere right in the middle?
So let me make sure I understood your question. So here I'm assuming the outcome, the larger the better. You are saying in some cases, you may not want it to larger the better or smaller the better. You may want like a middle the better. Is that what you mean?
Exactly. Yeah.
Right. So that, I guess in that case, what we need to change is the original, the value here. So here the value definition is we want the value to be the larger the better in terms of the response. But I guess in that case, perhaps we want to define like an optimal number, like say around the middle, then we can define the distance to the middle to be the outcome we are trying to maximize, like the closer to the middle, the better, or something like that. I believe it can be done like by doing some sort of twisting that way, rather than directly make it larger the better. Yeah, so related to that question, and in general, this mean thing can be an issue because we know mean is not sensitive to, it's not robust to, say, outlier or heavy tail and so on. And then one natural thing is, if you're just maximizing the mean, are we sacrificing people under the lower tail? Right? So, you could possibly have a small group of people on the tail because you say, oh, this treatment appears to have better mean for everybody. That's recommend this rule. However, there could be some people get harmed by using this rule. So then the natural question can be, instead of using mean, maybe using quantile or some other things. And indeed, things can be done that way. And we have some work on that. We can using conditional value at risk, which is really controlling your tail, essentially. There's some other thing, related to what you said is, what if you have something you hope to maximize, but you have some other thing you hope to control? For example, I want to control the blood pressure at the same time I hope to lower the cholesterol, something like that. And then you start to add certain constraint on top of this optimization. There's some work done in that direction as well. I think my colleague Dongling has some work in that direction too. That case is you have multiple things you are considering rather than just one thing you are maximizing. So there are several directions related to what you're asking, and I believe there's some work already doing something, but not exactly as what you said, but they're related work in different directions.
Excellent. Thank you very much.
Yep, sure.
So thank you. So I think so we already passed the time. So if you have any